Hi, hello students. In today's discussion, we're going to see about power diodes. Okay. Yes. Okay. Now look at here, the symbolical representation of power diode. You will not get any difference between this power diode and signal diode. Then what is power diode? See, power diode means these diodes are having capacity to handle large current and large voltage. Okay. So that's why it is called as a power diode. Look at the terminals of the diodes here. It is are same as like a signal diode. The terminals are here, it is represented as anode and cathode. Okay, now look at some of the features of this power diode. Okay, so normally these diodes, it requires 1 voltage to make it on. Okay, now current will always flows from anode to cathode, and this type of diode also, it does not conduct in reverse biased. Okay. Next one is the structure of power diode. Okay. You look at here, structure of power diode. Okay. Say a normal diode, it has only 2 layers, but here in power diode we have one more additional layer, that is drift region. Okay. Now why this drift region it is to be used? See, in power semiconductor switching devices, usually you will going to see this layer, drift region. Okay. Usually these regions are provided to reduce on-state losses. Okay. Now look at here, the N plus layer, it is to be considered as cathode, and it is the substrate. Substrate means body of the device, and the remaining layers of the device, it is to be constructed or developed over this substrate. And the structure of the arrangement, it is a vertical structure. Now why the vertical structure is selected? That is to increase the conduction area. Okay, conduction area. So now as the area of conduction increases, resistance will going to decrease. So with the decrease in resistance during conduction time, so it will going to reduce what? Power dissipation within the device. Okay, that is why the structural structure it is to be considered. Okay, now over the substrate, drift region is grown, and over that drift region, P layer is diffused. Okay, and look at the thickness and the doping levels. The plus sign indicates highly doped and minus sign indicates lightly doped. Usually drift region is lightly doped region layer. Okay, and one more thing, the thickness of drift region, how it is to be selected? Thickness of drift region, it is to be selected based on the breakdown voltage of the device. Okay. Then we'll see the VA characteristic. I think VA characteristic is familiar for you. This is similar like a signal diode. Okay. And VA characteristic, it is to be plotted between anode current and anode to cathode voltage. Okay. In x-axis we have taken anode to cathode voltage. In y-axis anode current is to be taken. Okay. In first quadrant the operation is forward bias, because here the positive voltage we will going to apply across the anode and cathode. Okay. Now as the voltage gradually you increase from 0, see initially no current flows through the device. Okay. A small current you will get, that is negligible. Those currents are in terms of milli or micro amps, and those currents are leakage currents. Okay. Now when the applied voltage, if it crosses the forward breakover voltage, see here forward breakover voltage, it is to be marked as 1 volt. Now after that a heavy current will going to flow through the device, and that indicates the turn on period of the diode. Okay, now look at here, during turning on period, a linear graph you will going to get. That means a sudden variation in anode current will going to get. Okay, means at that point, for whatever the increase in voltage, with the same uh, you will going to get the current. Okay, now look at the reverse bias case. Okay, at reverse bias, okay, it is the curve is similar like signal diode. Okay, initially no current flows. Okay, gradually if you increase voltage, negative voltage, if it crosses reverse breakover voltage, then device conducts. But remember, power diode also we never use under reverse bias. Okay, why? Because under reverse bias, current whatever flows through the device, that will going to make the permanent damage to the device. Okay. Next important one is switching characteristic of diode, and it is to be called as reverse recovery characteristic. This is very important from the point of examinations. If you see many old question paper, you are going to see a common question: explain reverse recovery characteristic of diode, or explain switching characteristic of diode. Okay, now look at here. Now what is this reverse recovery characteristic? Okay, say generally if you consider any switching device, what we will going to think, the switching transition period, that is from on to off or off to on, that will going to takes place at instantaneously, but it never going to happen. Okay, so it takes certain time for changing its levels from on to off. Okay, now what is the reason for that? The reason for that is stored charges at various semiconductor layers. Okay, say if you are able to remove those stored charges with a minimum time interval, then this time required to changing its positions, that also going to decrease. Okay, now look at here, a turn off period it is to be shown here. See, initially diode is conducting, so you are going to see here forward current, and after that the forward current is made to 0. Now before making 0, here some graph you are going to see. Okay, now the total time period for that the forward current, what it takes to make 0, that is to be taken it as TRR. What is TRR? TRR means reverse recovery time. Okay, now the entire reverse recovery time, it is to be splitted into as TA and TB. Okay, now what is TA, what is TB? Now TA is the time period which is to be required to eliminate excess charge carriers at drift region. Okay, next TB is the time period where the excess charge carriers at the main two semiconductor layers, that is at P and N, that is to be eliminated. Okay, so at the end of TRR, what will going to happen? The complete excess charge carriers at 3 layers, it is to be eliminated. Hence, forward current will going to reach its 0 value. Understood? Okay, this is what the reverse recovery characteristic. Next one is types of power diode. Okay, see, we have 3 different types of power diode: general purpose diode, fast recovery diode, and Schottky diode. The general purpose diode means whose reverse recovery time is high. Okay, it is about 25 microsecond. So because of this reason, the instantaneous switching, it never going to happen here. Okay, it takes certain time for that. So because of that reason, this type of diodes you can use only for low speed applications. Okay, now it can be operated up to 1 kilohertz, and their ratings are from 1 amp of 50 volt to 1000 amp of 500 volt. Okay, next, fast recovery diodes. Okay, these diodes have reverse recovery time lesser than general purpose diode, that is about 5 microsecond. So you can use this one for high speed applications. Okay, like chopper and inverter circuits you can use. The last one is Schottky diode. Okay, now what is the difference about this Schottky diode and other type of diode, that you can get here at the structural diagram. See, this is the structural diagram of Schottky diode. See here in structural diagram, you can see the P layer is replaced by a metal layer. So metal layer, it is to be considered as P layer. Okay, now because of this usage of metal layer, the excess charge carriers that can be eliminated. Okay, now when excess charge is eliminated, what will going to happen? Reverse recovery time will going to decrease. Okay. Also here there is absence of what? Drift region, right? So the fast switching that can be able to achieve. Okay. Now where the switching Schottky diode you can use. See here there is symbol of representation of Schottky diode. So you can use Schottky diode in feedback path, or also you can use this one as a freewheeling diode. Okay. Now applications of power diode. Okay, it is used to be used in uncontrolled rectifiers. It is used as a free feedback and freewheeling diodes in commutating circuits, half control converters and half bridge inverters. We are going to use power diodes. Okay. Next, one special type of diode we will going to see here, that is silicon carbide SiC diodes. What is SiC diode? So SiC diodes are nothing but here instead of silicon and germanium we will going to use SiC carbide as a semiconductor. Okay, that is the difference. Okay, and the features of this is it has very low reverse recovery time. Okay, then the features here, they have no reverse recovery time, their switching is extremely fast, switching behavior is unaffected by temperature, very small power loss, high reliability, then advantage high efficiency, compact in size, high switching frequency, reduced small electromagnetic interference. Applications: energy saving power supplies, efficient solar energy, welding equipments, air conditioning, transportations. Okay. Next, silicon carbide Schottky. Here also you will going to see Schottky of silicon carbide. Same thing here also, one of the layer we will going to use metal layer, and the advantage of this one is the switching speed here it's very high, because the almost reverse recovery time is absent for this, and it is a highly reliable and rugged, strong in construction, reduced cost due to no additional cooling required, high power density, switching losses are very low, stable at high surge currents, operate at high frequencies. Okay. Then next we will going to see diode as a switching device. Okay. Say for simplification purpose here, switch S1 is represented along with the diode. Okay, and load is to be connected as R and L. Okay. Now whenever switch S1 is closed, load will get the supply, and at that time load current will going to flow. Okay. Here there is a waveform of supply voltage and load current. Okay. Okay. Now for that you will going to get these equations, load current and inductor voltage. These are the two important equations. Okay. Okay. Next one is switching circuit, diode switching circuit with the freewheeling diode. Okay, a freewheeling diode we will going to use along with the inductor load. Okay, freewheeling diode, it will going to remove the charge storage at the inductor. Okay, when it will going to remove, that is when switch is open, the stored energy at the inductor, that will going to that will see the path to discharge. Okay, usually if the freewheeling diode is absent, means it will going to pass through the diode, so diode will going to damage. Okay, to avoid that we need to use the freewheeling diode. We look at here the current waveforms. The first waveform is the load waveform. Now out of this, see, whenever the switch is open, that is at time period T2, see, at that time whatever the current in the circuit, that is due to stored charge at the inductor, that will going to flow through the freewheeling diode. Okay, yes. Okay. Next one is the rectifier. Okay, rectifier, you know, rectifier, it converts AC supply into DC supply. Okay, now the one of the major drawback of this rectifier, diode rectifier, is output is uncontrolled. Okay, say diode rectifier, it does not have any control over the outputs. That is the disadvantage, and it performs the rectification function. See, these are the different types of rectifiers. We have single phase diode rectifier and 3-phase diode rectifiers. Okay. Next, the advantages, disadvantages and applications. Advantages: simple circuit available at all power capabilities. No control circuits are required. Single chip rectifiers are available in single phase and 3-phase. High frequency as well as low frequency rectifiers are available. Low cost. Output voltage is uncontrolled. Power flow is unidirectional. High ripple content for single phase rectifiers. These are the disadvantages. Next, applications. UPS, simple electronic circuits, low power battery chargers, simple and low power DC supplies. Okay. Yes, students, with that, okay, I will going to finish a power diode. Okay. Yes. Thank you for watching.